Hello everyone, in this video I will be starting the group 13 elements, that is the boron family. Okay, now the boron family consists of elements of like boron, aluminium, gallium, indium and thallium. Okay, it is the group 13 elements and these belong to the PBlock. Okay, now among these elements, first of all the elements are boron, aluminium, gallium, indium and thallium. Okay, these are the elements of boron family. Okay, now boron is a typical non-metal. Okay, aluminium is a metalloid. Okay, this is a poor metal. And indium and thallium are almost exclusively metals. Okay, so among the boron family, boron is a typical non-metal. Okay, while aluminium is a metalloid. Okay, gallium is a poor metal. Okay, by poor metal I mean some of its oxides are amphoteric. Okay, it has some properties of non-metal, very little properties of being non-metal. Okay, but indium and thallium are almost exclusively metals. Okay, now the electronic configuration for boron is the electronic configuration I will write over here. The electronic configuration for boron is 1s2, 2s2, 2p1. Okay, for aluminium it is 1s2, 2s2, 2p6, 3s2, 3p1. Okay, for gallium it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p1. Okay, for indium the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p1. For thallium the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 6s2, 6p1. Okay, these are the electronic configurations of each of these elements of boron family. Okay, now you can see that the general electronic configuration. Okay, when we would consider the general electronic configuration, you can see that every element of boron family has ns2nt1 configuration, outermost valence cell configuration. For every element it is ns2nt1, it is ns2nt1. Okay, you can see here ns2, ns3, ns4, ns5, ns6. Okay, so the electronic configuration, the valence shell electronic configuration, electronic configuration of these elements is ns2 and B1. Okay, which you can see from this, from these electronic configurations. Okay, now the next point is the atomic radii. Okay, now first of all, let me grab me this part. Because for finding atomic radii, you will need these electronic configurations. Okay, now atomic radii. Okay, now for the atomic radii, boron has the least atomic radius. Okay, I told you in the previous video that the first element of each of these family, okay, has a very small size. In fact, it has the least size among all the elements. Okay, so atomic radii for boron is the smallest. Okay, now what happens is that there is a discrepancy in the atomic radii. Now you know that atomic radii, when what is happening, the number of shells are increasing. Okay, what has happened here? Here there were 3 shells, here there are 5 shells, here there are 8 shells. Number of orbitals, okay, the rings which I told you in the previous video lecture. Okay, these rings are increasing. Okay, the orbitals are increasing. Therefore, the size of the atom must be getting bigger. Okay, if this is the nucleus over here, okay, then these rings are getting bigger in number. Okay, these rings are getting bigger and bigger in number. So as the number of orbitals or rings would increase, okay, the size of the atom is expected to increase. Okay, you expect it to increase. But what happens is that in case of aluminium and gallium, okay, gallium is radii for gallium is less than aluminium. Okay, now why is it so? Why is that despite having 8 orbitals, okay, for gallium, the atomic radii for gallium is less than aluminium? It is not. It is quite amazing. Okay, so what happens in this case is that there is an, you can see this, the answer to this is the electronic configuration of aluminium and gallium. Okay, now you can see that there is addition of additional d orbital in this case. Okay, what happened is that there was a new d orbital added in case of gallium. Okay, now these d orbitals offer poor shading. Okay, what do we mean by shading? Shading means protecting. Okay, these d orbitals do not protect the outermost 4s2 4p1 electrons. Okay, now how do these orbitals offer shading? Okay, now these orbitals offer shading in this way. Okay, so consider this. I am drawing the diagram for gallium. This is the nucleus. Okay, and these are the orbitals. Okay, these are the orbitals. Now, for the first it is 1s2, therefore there are 2 electrons. Next it is 2s2, again there are 2 electrons. Next it is 2p6. So 1, 2, 3, 4, 5 and 6. Okay. Next it is 3s2. So 1 and 2. Okay. The next it is 3p6. So 1, 2, 3, 4, 5 and 6. Okay, then 3d10. Okay, now 10. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Then 4s2, there are 2 electrons over here, and 4p1, there is 1 electron over here. Okay, so what happens is that how do these orbitals offer shielding? Okay, now these electrons, as you know, they move in these orbitals. Okay, so these electrons protect the entire, they create the entire sphere, okay, of negative charge. Okay, just imagine that there are so many, you can imagine that there are so many spheres of negative charge. Okay, like this is one small sphere, then one bigger sphere, then another big sphere. Okay, so these spheres, okay, protect the outermost these electrons. Okay, they protect these electrons. Okay, each sphere inside will protect the electrons outside. Okay, these electrons. Okay, these protect them, these inside spheres. Okay, so what happens is that, but in case of d orbitals, okay, d orbitals have a poor shielding effect. Okay, they do not protect these outside electrons. Okay, because they are very big. You can see that this d orbital is quite big than this s orbital, and it is very far away from the nucleus also. You can imagine this is this big, so it will not protect that electron. Okay, which is outside that. Okay, so these d orbitals offer very poor shielding. Okay, so what happens is that this 4s2 4p1 electrons, these electrons, okay, of 4s2 4p1, they are affected, they get attracted by the nuclear charge present, the positive charge. Okay, and what happens is that they shrink or they move towards the nucleus. Okay, they move towards the nucleus. Basically this thing shrinks. Okay, so you can see that for aluminium the nuclear charge is how much? The aluminium, the positive charge is plus 13 inside, but for gallium it is what? 10, 8, 18, 28 and 31. Okay, so here the nuclear charge for gallium is quite large than aluminium. Okay, so this would have a more effect on these electrons as compared to outside electrons of aluminium, the nuclear effect of nucleus on the outside electron of aluminium. So these electrons will shrink. The cause of this shrinking, so this shrinking will cause the radius of gallium to be less than that of aluminium. Okay, because of poor shielding effect of the d orbitals. Okay, so we will note down this point. On moving down the group, the atomic radii is expected to increase, okay, but due to poor shading effect of d orbitals, okay, radius of gallium is less than radius of aluminium. Okay, so what is the trend for atomic radii? East is boron. Boron is greater than gallium, is greater than aluminium, is greater than indium, greater than thorium. Okay, so this is for atomic radius. Okay, now the next point is, the next physical property is that of ionization enthalpy. Now, ionization enthalpy values. What is ionization enthalpy? First of all, ionization enthalpy is the energy required to dislodge an electron from its shell. Okay, to dislodge any electron from its shell. Okay, this is the ionization enthalpy. Now, again, the trend for ionization enthalpy is also not smooth. Okay, what do you expect? You expect that as the size increases, as the atomic radii increases, the ionization enthalpy must decrease. Why? Because the outermost electrons, okay, we are interested in finding the ionization enthalpy, IE, of outermost electrons. Okay, so for outermost electrons, these outermost electrons are far away. As the atomic radii increases, these outermost electrons get away from the nucleus. Okay, as they will get away, the energy required to dislodge them, okay, will be less, because this energy. Why do we require energy to dislodge these electrons in the outermost shell? Because these electrons are under the effect of this nucleus. Okay, this electron is there is a electrostatic force of attraction between this positive charge and this negative charge. Okay, so these electrons are under effect of this nucleus. So to dislodge this electron from this shell, to dislodge this, we need to provide energy. Okay, so we need to give energy to dislodge this electron. Now, as this electron will move far away from the nucleus, okay, since this is electrostatic energy, this energy is directly proportional to 1 by radius square. Okay, in electrostats you must have studied. So as the radius increases, the energy required would decrease. Okay, so you expect that ionization enthalpy to decrease when you move down the group. Okay, but it does not happen. What happens, as I told you, because this decrease is not smooth, because the atomic size increase is not smooth. We just saw that the atomic size of gallium is less than that of aluminium, okay, which was a discrepancy. Therefore, similarly, ionization enthalpy, for this reason, the ionization enthalpy of gallium is equivalent to that of aluminium. Okay, so for boron, it is the maximum. For aluminium and gallium, IE of gallium is equivalent to IE of aluminium. Okay, because of the atomic size. Okay, now again, for this case, this should have been, what should have been, what is expected? It is expected that IE of gallium is less than IE of aluminium. Okay, but this does not happen. This is correct. Okay, and for indium, what is expected? Expected that IE of indium is greater than IE of thallium. Okay, but again, this is not true. What is true is IE of indium is less than IE of thallium. Okay, this is the correct one. Now again, why does this take place? Because again, in this case also, it is, see, when we move down the group, the only factor which is different from up the group and down the group is the presence of D and F orbitals. Okay, see, here there is no F orbital, but here there is an F orbital in indium. In thallium. Indium does not have any F orbital, but thallium does have an F orbital. And again, these d orbitals and F orbitals offer poor shading effect. Okay, again, the reason is poor shading effect. Therefore, this is the case. Now, so the actual trend in this case for IE is, the actual trend is boron. Okay, boron has the highest ionization enthalpy. Then it is aluminium. the ionization enthalpy is 577. Okay, kilojoule per mole. Then it is equivalent to gallium. The ionization enthalpy is 579 kilojoule per mole. Okay, then the ionization enthalpy is of first of all, the trend for IE is, okay, let me write it over here. Okay, let me write the trend over here. The trend for IE is, see, for boron, the IE is 801 kilojoule per mole. For aluminium, it is 577 kilojoule per mole. It is 579 kilojoule per mole. For indium, it is 558 kilojoule per mole. And for thallium, it is 589 kilojoule per mole. Okay, so it is boron is the maximum. Okay, then it is thallium, then it is gallium, then aluminium, then indium. Okay, this is for the IU. Now this was about, now for electronegativity, the next property is electronegativity. Okay, but before that we must write for what was the cause of abnormal property of ionization enthalpy. We will write it down that IE of gallium is equivalent to IE of aluminium and IE of indium is less than IE of thallium because of poor shielding effect of D and F orbitals. Okay, so the poor shielding effect of D and F orbitals is the cause of this discrepancy in ionization enthalpy. Okay, now for electronegativity. Now electronegativity, again, when we move down the group, okay, the electronegativity must decrease. Okay, because what is electronegativity? The tendency of nucleus to attract the electrons. Okay, so electronegativity because attack other electrons, basically outside electrons. So what happens is that as the atomic radii increase, the electronegativity must decrease. Okay, because the effect of nucleus beyond these orbitals would be less as the atomic radii increases. Okay, but again, due to the abnormal increase in atomic radius, the electronegativity values also does not decrease smoothly. Okay, now, so the atomic electronegativity for boron, the values for electronegativity is 2.0, for aluminium it is 1.5. The electronegativity value for aluminium is 1.5, then it is for gallium 1.6, then 1.7, then 1.8. So you can see that the electronegativity value should have decreased, but it increases marginally because it increases marginally because of abnormal atomic radius. Okay, so the reason for it is, first of all, the trend and then the reason. Okay, so the trend for atomic electronegativity is boron is the highest, then thallium, then indium, then gallium, then aluminum. Okay, this is for electronegativity. The electronegativity must decrease, but it does not happen because of discrepancy in atomic radii. Okay, atomic electronegativity must have decreased, okay, but it does not happen because of discrepancies in atomic size. Okay, so that's all for this video regarding the physical properties of boron family. In the next video I will tell you about the chemical properties of boron family. Okay.